Okay, let's get started. Welcome to the fifth lecture in Discrete Math. The next lecture will be the last one, and today we are going to discuss, well, besides other things, the third assignment for your home class, for your home task. So this will be a small programming assignment, also graded automatically. Well, at least if it happens to be possible. So the details will be published on the web page and sent to you by email probably tonight, and you will have a little less than a week for this task. Well, it's really short. So I think the optimal solution is like 5 lines of code, but this is something like Python hacking. If you do it more naturally, you will get a longer program, but it is easier than the first assignment, of course. So about the first and the second one, I will comment a bit at the end of the lecture. So if I forget, please remind. So the first topic for today is the system called Network X. It's a Python library for network analysis, and we'll talk. Well, network means graph. It's just at this lecture it will be just a synonym of the same, and the running series of examples will be connected to social network analysis, and we'll see a sort of toy but real data set from Facebook, which will show us how to do this. And the second half of this lecture will be devoted to one interesting problem in graphs, which will be also, well, there will be interesting complexity results, which we'll see at today's lecture. This will be the problem of isomorphism and subgraph isomorphism. So run an example, social network analysis. So what is this SNA? So we study graph structures which represent social connections. So the very basic example is, say, friendship in a social network. So it's going to be, what is it? It is an undirected graph without loops and without parallel edges. So between two members of the social network, there could be at maximum one friendship relation. You cannot be, say, twice a friend of another one. Also, loops are probably not allowed because, well, a person is not considered a friend of, say, himself. But I think in Vkontakte at some point it was possible to do so, to make friends or even establish a relationship between yourself. But I don't know whether it was a bug or a feature, but nevertheless. So it's just a graph. It's an undirected graph. But this is not the only, say, possible situation in social network analysis. There could be directed situations, like, for example, you have some big object, for example, some big entity or, say, a celebrity, and you have people who get subscribed to it. So you subscribe, say, to Wall Street Journal. This is a only one-way relation because the journal even doesn't know about you. So this is a situation of directed edges in such graphs, and also edges could be of different sort. This is also possible. So the social network is sort of graph-based structure. It could be more complicated than just a graph, but it is a graph-based structure. So SNA as a branch of research, branch of science, is on the border of discrete math. It's an exact science, logic, and sociology. And also, of course, data analysis, because social networks are not just graphs, they're big graphs. Vertices are actors, say, people, social entities, etc., and edges represent, also they're called links or ties, and vertices are called nodes sometimes. These are all synonyms, represent various relations between actors. They could be symmetric, asymmetric. The standard example is friendship relation. So we're going to talk a bit about graph parameters today. So by graph parameters, we mean some, say, global characteristics of a graph which can be computed using this graph. So, for example, number of vertices, number of edges. This is something which is just on the top, but deeper you will have something like, for example, average degree of a vertex, which represents, in a sense, the density of a graph. So how many friends typically a person has. So another possible thing is, what is the probability of an edge? So if you take two random people, how probable is that they're friends? But there will be some more interesting parameters. There is also an interesting parameter connected to social networking, which is the diameter, with the famous 6 handshakes conjecture that between any two people on Earth there is 6 path of length 6 or less. So, and we're going to get acquainted with special software, but here it is said that it's for calculating the parameters. It's actually for working with graphs, as they call it, network. And we'll notice that how some of the graph parameters, well, we'll actually have one basic example, have specifical behavior in the case of social networks, say if compared to a random graph. So we'll see that properties of these real world graphs, they could be different than something which you can generate theoretically. And we shall see this on the example of the so-called clustering coefficients, which tend to be quite high. So we'll give the formal definition later, but the idea of a clustering coefficient is as follows, that as you can easily see, in all reasonable definitions, the social network is rather sparse. It's not dense. So the network is very big. There are, say, millions of vertices, but say the typical degree of a vertex, the typical number of friends of a person, well, it's something like 1/200 or something like that. And the probability for two people to be friends is also, well, it's close to 0. If you take two random guys somewhere on Earth, then probably they do not know each other. But on the other side, you see that there are clusters. That means that if, say, several people know each other, it's quite probable that they're all, say, acquainted at least. And there's a high probability that they could be friends. Friends here in the sense of this formal social networking friends. So this could be measured, and we'll see how this measure works in real play. And this reflects the following idea, which can be formalized as follows, that friends of one person are much more likely to be friends also. That if you have, say, just random two people, then the probability that they are friends is close to 0. But if you have, say, two people who are friends of a third one, then they are quite likely to be friends. Well, it's not that they will be friends with probability 1 or close to 1, but it will be something like, I think, 0.6 or something like that. So it's much higher than just at random. And this is reflected by the clustering coefficient. So on the other side, it is a bit of paradoxical that how could you imagine a clusterized network? So the intuition that it should probably, say, really clusterized. So it should probably split into several, say, subgraphs, which can be even not connected with each other. Groups of friends or something like that. This comes from the intuition of clustering, but it's not the case for real social networks, because it happens to be tightly connected to the famous 6 degrees of separation, or 6 handshakes. They claim that any two people are connected with no more than 6 social connections from one to the other. So in a sense, it's clusterizing without clusters. So the network is it's sparse. There are very few edges if compared to the number of vertices. The number of edges is like, it grows like n, like the number of vertices, not like n square, which is a complete graph. But it clusterizes, so this means that people tend to, if they're friends of one guy, then they also tend to be friends. But on the other side, what they call the diameter of the graph, so the maximal distance between two people, is also quite small. So it's these graphs have, say, rather controversial statistical properties. So this is called the diameter. The diameter means that you take any 2 points, you measure the shortest distance between them, and then you take the maximum for all pairs. So this is a maximin type parameter. It also can be computed, but this is easy to compute, but requires some time for all these things. We'll see it. And in our examples, we're going to refer to what is called SNAP dataset. So it's called Stanford Network Analysis Project, SNAP. And dataset includes, well, it was taken from Facebook. Of course, it's not the complete Facebook data set, well, for two reasons. The first one, that it is enormous, and the second one, that there are problems with privacy. So, of course, you can anonymize the real data and replace, say, real names of people by some identifiers which cannot be easily de-anonymized, but the problem is that if you have the complete Facebook data set, it's prone to structure mining. So if you have this, we'll see it in the second half of today's lecture, if you know some subgraph inside it, and you can know it just by analyzing your own friends, then you can find this pattern inside. And then you can explore this network and actually de-anonymize everything. So this means that the real data set, the real, say, database which is inside Facebook, it should not be open for general public to study, even in an anonymized form. And here, this is what's called ego networks, and we'll use this notion inside your third home task. What is an ego network? So you take a person inside the social network and consider all his friends. And then you see the friendship relations among them. So it's a subgraph, and you just take this part. And here they take 10 users, and they took the ego networks of them. Of course, this will not taken at random, because otherwise you will just have probably, say, 10 disconnected graphs. Here, these 10 people, maybe they're not friends of each other, but they could be friends of each other. So these ego networks, they intersect, and this represents a part of the real, say, social network graph. Of course, since there are 10 designated points which behave differently, because for these 10 people we know all their friends, but for other we only consider their friends among the friends of these guys. So this means that this will be not actually an exact model of a social network, so even not a baby model. It will have some biases based on the fact that there are 10 designated nodes inside it. But nevertheless, we'll see that it models social network behavior in quite a good way. So, and this is a small data set which can be then downloaded from Snap, and it will be included in your home task. We'll use it. And it's relatively small, and of course the data is anonymized, and instead of names you will see numbers there. Network X. So we'll use Network X as a Python library for analysis and visualization of graphs. It's free software, of course, released under BSD new license, capable of handling real-world data sets. So as they advertise, like 10 million nodes is okay for them, and it will not fail on that. And this means that you will have something like 100 million of edges. You see again, this one says that your graph is quite sparse, that the average degree is something close to 10, because otherwise you will have to square this 10 million, which will be huge. But in real networks is the usual case. And therefore, well, at one of the previous lectures, we discussed how a graph can be represented. And the usual representation, which you can sometimes find in literature, is by table of connectedness. So you just take a matrix where you have Bij is a 0 or 1, depending on whether there is an edge from I to j. Here it is the bad way to do it, because the network is sparse, and you will have to keep a huge matrix, a square size matrix, mostly of zeros. So here the internal representation, well, you can open this network X and see how it works. It's something like representing the lists of vertices connected to a given one. So be much more economic in the sense of memory. It will use linear memory. And it's also highly portable and scalable. So this is how it is installed. Just you take network X, and there are two other libraries which are called matplotlib and scipy. These two are for visualization only. So they're not needed for computing using network X. For analysis, these are used for drawing pictures. Matplotlib is the standard plotting library. And then you import it like that. I imported it as NX just for brevity. You can just say import network X. So how do you get started? You represent a graph by initializing it. You introduce a new graph, and then you just add edges. You can add edges. There is also a command for adding vertices. but it's not necessary unless your vertex is isolated. Because if you have, if you add an edge, and the vertices of the edge can be arbitrary. There could be numbers, letters, strings. This is the virtue of the fact that Python is really type-free. So when you add an edge and it sees that this edge includes a vertex which did not exist in the graph, it just adds it silently. So here the graph is undirected. So if you add CA, automatically you also, in a sense, add AC. So the symmetricity is maintained inside this graph structure. Yeah, they could be arbitrary types, strings, numbers. Also, it can handle other types of graphs. For example, for a directed graph, you just use dgraph instead of graph. And then when you add an edge, you will add a directed edge. Also, the edges can be weighted. So what means the weighted graph? That each edge receives a number which is called its weight. And the weight represents something like, for example, if your graph is a graph of roads or a geographical information system, it could be time or some other measure of cost of traversing this road. And you just can add the weight as an optional parameter to add edge. And the same works for dgraph also. In geographical information system, you can have directed situations. So network X is capable of reading the graphs from files, or data sets, by a standard thing that you can use it. There will be a file called Facebook combined, and you can read it like this using read edge list. This is quite convenient. However, in our running example, and you will see it, we'll formally describe it in the definition of the homework, we'll use another way of doing this. So the file will be pre-read by the testing part, and you will just be given your graph as a list of pairs of vertices, which is the list of edges. This is done for some reasons that I will tell a bit later. So graphs as abstract objects can be nicely represented geometrically. And sometimes, even without formal analysis of graphs, it can be interesting to see how the graph looks like, even if it is huge. And we'll see this. And this is called visualization, and network X can visualize graphs on the plane and also in 3D. So this is how it basically works. And we see that in our small example, we see something like that. So here inside your vertices, maybe it's not that clearly seen here, but you have A, C, B, and D. So this is a directed graph. And notice that if you have edges, well, they're not parallel, but they are sort of on different directions between vertices B and C. Here it's represented as an arrow with and an edge with two arrows. These are actually two edges. For real data, for this FBGR, it's a graph taken from this SNAP dataset. We remove labels because otherwise they will just overpopulate our picture, and we get something like that. And you see that here you have visibility of these clusters, well, which look like there should be 10, say, points which generate these clusters. But you see that these are all also connected to each other. So we have two, say, big groups of people, and the small and the big one, but there are also some connections between them. So here you, at this representation, you probably can see the, say, how the social network graph looks like. No, not the network itself, but it's part which is generated by 10 vertices. So how do these graphs tend to cluster? How can we measure that? So take the probability of for a pair of vertices to be connected. So how it is calculated is just standard, say, the most, say, simple notion of probability that you just take the number of edges which is inside the graph and divide it by the maximal possible number of edges, which is n multiplied by n minus 1 divided by 2, right? Just the total number of pairs of different vertices. And in general, this is quite low. In social networks, it should be very low. because random people are usually not friends. In this data set, it will be higher because these are ego networks, so these are not random things. But however, if A is a friend of B and C, then probably there is a friendship relation between B and C. It becomes much more probable. So it's so-called conditional probability. And you can measure it using the global clustering coefficient. So you take a triplet, which is a pair of edges going from one vertex, and a triangle is just a triple. And the global clustering coefficient is 3 multiplied by the number of triangles divided by the number of triplets. So you see how many of the triplets get realized as triangles. So how many of the triplets have this third edge? And you multiply by 3 because each triangle is actually 3 triplets. Each vertex, so you have this BAC, ACB, and CBA. And this global clustering coefficient is the probability of random triplet to be closed into a triangle. Also the local clustering coefficient, or we count only for a given vertex. So let the degree be k. The total number of triplets is as follows. It's the number of vertices connected to A. And it is the following ratio that you take the number of pairs which form a triangle and divide it by this. And then you put 2 on top. The local clustering coefficient. Oh, no, yes, 0 by 0 division, yes. If there is an isolated vertex, then this is undefined. You don't know how does it tend to cluster, because local clustering coefficient actually measures not the clustering of A itself, but the clustering among its friends. So if you have no friends, you get it. So this is an example here. Of 2 divided by 3. And you can, network X has a convenient interface. So for example, here you calculate the average clustering coefficient. You take the average of local clustering coefficient. This is also another parameter of the clustering. And you just take the special function which just does the job for you. You don't have to do it yourself. So here is an experiment, how we can try to do this. Let's just look at the code. Well, it's a real listing of real code. I stripped it from comments just to fit it on one slide. So you import network X. You import the function random. This will be used for generating a random graph. This is used for, say, visibility only. Inside network X, there are functions which generate random graphs, and not that stupid as here. So you take this real data, in a sense, from this Facebook combined text file. You calculate the average clustering coefficient. You print it on the console. Then you count the number of the edges. You take the maximal possible number of edges and calculate the probability, which is the real number of edges divided by the maximum number of edges. And then you generate the random version of the graph. So you see what happens. Random takes a random number between 0 and 1. So if you say if random is associated with an edge probability, this means that you do this with probability edge probability. So what happens here? We take our graph, we measure the density of the edges there, the probability of for 2 vertices to have an edge, and then we try to simulate our social network by the following idea, that we just put these things at random. So this is called the Ereduscrania random graph. It's the easiest, simplest way of making a random graph. Here, all the edges are independent. And this will kill the idea, actually. And then you calculate the average clustering coefficient, and you return it. So let's see the results of the experiment. So the first is deterministic, that it's just a concrete data set, you will return the average clustering coefficient. For the second, of course, the results will be random. If you run this program, we'll get slightly different result. But of course, since the law of big numbers will guarantee you that it will be close to what you will see here. And of course, unsurprisingly, you will get the following. So the average clustering coefficient of the original graph is something like 0.6. It's the probability. So if you have a guy, and this is the probability of his friends being friends. It's not 1, It's not close to 1, but it's something like half. It's 0.6, about more than a half. In the random graph, you'll have 0.01, which is much less. It's 60 times less. Because, well, it's random. And this probability, so this is actually this random graph average clustering coefficient is going to be close just to the probability of an edge. It's basically the same because all of them are independent, and the probability of two friends of someone being friends in this graph is the same as the probability of two random people being friends because of independent. What is the moral of that? That social networks tend to cluster more than a random graph with the same probability of edges, unsurprising. And this is the motto of this part of the lecture, that you have to be very cautious with stochastic modeling of social graphs. So when you try to model some sorts of social behavior, of course you wish to, well, for many reasons, you usually do not have access to real-world data sets. This is a toy example, but for real-world it's problematic, and even more problematic if you consider, say, physical interactions between people. Not social networks where you have this formal friendship relation which is stored in some database, but say people who are friends in real life, or people who just come across each other at work and public transit and stuff like that. This is hard to model because you of course want to model it by a randomly generated graph. Here you see that the first idea to make all the edges independent was bad, and it gave us another parameter, which is a clustering coefficient, which was extremely different. The actual problem is that it's sort of a chase. So you could ask, okay, but could we accommodate for this parameter also? Try to make them dependent in a sense and obtain a random graph model with dependent probabilities of edges, which will make this parameter also close to that. Of course, it's possible. In this course, we are not discussing that because this will well, first, we don't have time, and the second reason is that we will need some more probability theory background for that. But there are models like Stroger's model, for example, which accommodate for this. But then one also could invent another parameter which would also fail. So it's sort of the real network of people eludes many of these approaches. And this jeopardizes the, say, prognostic power of these methods, because your idea is that you should construct a random graph which models the real network in the sense that it has the same parameters from one fixed set we can really compute. Like of course, you have the same number of vertices, you have the same probability of edge, the same density of edges, you can have the same clustering coefficient or close one, and so. But when you try to predict a new parameter, you have no grounds that you won't fail. So this does not mean that you should not use these methods, and statistical modeling of social graphs is quite a big area in social network analysis, but one has to be extremely cautious here. And all the results, they are sort of, we should double check them, otherwise just obtain predictions which will not happen, and the real network will behave in a different way. So again, another example of network X, suppose we want to check 6 handshakes. Diameter, again, we have a special function which computes it. And it takes quite long. And this is predictable because if there are no pre-computed informations about distances in the graph, and this can be done in network X, there is such specific vehicles about that. It computes something which is called eccentricity. We'll not discuss what is eccentricity, but it's useful for computing the diameter. And then it yields the output 8. Well, it's not 6, but the problem is that it's not a real friendship graph. You have only eigennetworks networks, and there could be shorter connections which go outside this subgraph. It's quite a good result. So again, you can compute distances. So the distance is the length of the shortest path. Diameter is the longest distance. So again, you will have this computing the shortest path length. And in directed graphs, it's also directed. Distance from A to B could not be the same as B to A, because there could be directed edges, and sometimes even B is connected to A, but not vice versa. Where with this function, if there is no path from A to B, in directed case, no directed path, no oriented path, then it will just throw an exception. Mathematically, it should return something like infinity in this case. But here it throws an exception. It's unfortunate. So to be on the safe side, first you have to check that there exists a path. This is done by the has path. And then you can find the length of the shortest one. So in preparation for homework 1, we'll start thinking about homework 1. What is going to be this task? It will be the following. You will have this graph in the Facebook data set. I'm just now speaking it in words. You don't need to memorize this, because this will be for the first home assignment. This will be published on the GitHub page, so you will just see how should it be performed, both the informal description and the technical details. The idea will be as follows: you will be given this Facebook data set, the concrete one, and also you will be given a list of vertices, which include these ego network centers, the 10 vertices which were taken at the ego network centers, and plus one extra vertex, which we will call the imposter. It's just one of the guys who was not given as the center of an ego network, but also inside this list. Just a friend of one of these. And your task will be to determine who is the imposter. So why I did so? Because computing, say, standard graph parameters using network X is not an interesting task, because for most interesting graph parameters, network X just has some nice functions which compute them. So this will be meaningless in a sense. And doing experiments like this also is meaningless, because here I generated, at least the random graph was generated by hands. But really, even the generation of the random graph can also be performed automatically. So this is all automatized. But the problem which I propose for the home assignment, you will have to really deal with the graph. So how can you find out which vertices are the ego centers? Well, if it is the real set of ego centers, then you have the following property, that any other vertex is connected to at least one of them, right? And this is how you can determine the imposter. If you remove some vertex which was not the imposter, then the remaining will be not a set of ego centers. You will have a problem with connecting them. So, of course, you can think that this is a stupid home assignment, because in it you will have a fixed data set and fixed questions, so we'll have actually a fixed answer. And by knowing it, you can actually Google it. You can just find, when you open this Snap data set on Snap, you will see which vertices were taken as the ego centers. But you should do it honestly, because in the tests it will be randomized. It will be shuffled. So the vertices will be interchanged. And therefore you need to do it. And therefore you will, in your program, you will not read it from the file, but it will be given by the testing program. Because otherwise you will just have only one, and you can just make trigger. So more information about network X is available in the documentation. So if you need some function which was not on this slide or somewhere else, you will just find out in the documentation. And so preliminary, I wish you good luck with this home assignment, but the details will be published tonight. So this is the end of the first half of the lecture, which just we discussed network X. I hope I've convinced you that it's quite a convenient way of representing graphs and working with graphs in Python. And now we're going to more theoretical business. Yes, again, about the home task number 3. There will be an automatic grade as in home task 1, so the same in GitHub. Again, formally, you are not restricted to using Python and network X. So theoretically, you can use any other tools in Python of your wish, or you can do it manually, which will not be that convenient. And the autograder on GitHub will also, of course, take care of that. because the autooperator does not invoke network X, it's flat. And if you prefer other languages, like C, Haskell, or something else, you can submit it by email. So now we're going to some theoretical questions, and we're going to discuss algorithmic problems connected to isomorphism and the notion of subgraph. So first, let's recall what an isomorphic graph. I don't remember whether we gave the definition formally, but I think your general mathematical intuitions should suggest you a correct understanding of what isomorphic structures are. So sometimes the graphs look different, but they're essentially the same. So these are copies of the same graph, but they're differently drawn. And you can describe them as a triangle and a quadrangle sharing a common edge. Sometimes it's a different situation. So these graphs look much more similar, but they're essentially different. Why? Well, because this leaf, this vertex of degree 1, on the left-hand side is connected to a quadrangle, and here is connected to a triangle. And you cannot reorganize the vertices of one graph to map it directly on the second one. Okay, so they're not isomorphic. And this is the formal notion of isomorphism. Well, it looks scary, but you will see that it's quite easy. So you can establish a one-to-one correspondence between vertices of one graph and another graph. All this will be published on the web page, of course. This one-to-one correspondence keeps edges in both directions. And here you can understand it as enumeration. So you enumerate the vertices of first graph G, the second graph H, and so if vertices ij are connected in G, then they should be connected in H, and the other way around. And isomorphic graph, they can be seen as different just representations of the same graph. It's a shuffle of the vertices. So here, this is how they can be enumerated. So you can, if you can see that there is a quadrangle 1, 2, 3, 4, and here the same 1, 2, 3, 4, and the triangle is 3, 4, 5. So you see that if there are two vertices, 3, 4, which are connected on the left, the same are connected on the right. Two vertices not connected, 1, 5, they're red here. They're also not connected in the other graph. So this is a one-to-one mapping. This is called isomorphism. And so if such numberings are possible, then the graphs are called isomorphic. And the isomorphism itself as a mathematical object is this correspondence between which connects vertices of the same number. So what could be the algorithmic complexity of checking whether two graphs are isomorphic? How do you see? If you are given two graphs, how can you check that they are isomorphic? What is the level of complexity of this problem? Which class does it belong to? Well, easily. From the classes we have discussed. Or what classes do we know? Basically two complexity classes, right? So the larger class is NP, right? Yeah. Is this problem NP? Non-deterministic polynomial algorithm. Of course, yes. Because you can just non-deterministically guess this isomorphism. You just take two graphs and you say, okay, I'll take vertex 1, I will connect it to something. Vertex 2, I will connect it to something. It's a non-deterministic guess. And if the isomorphism exists, then the angelic choice will show you that it really exists. Or in the definition with hints, you can just ask for a hint, and the hint will be the isomorphism itself, as a set of pairs. And you check that it is really an isomorphism, which means that it is a bijections one-to-one correspondence. And if there is an edge here, then there is an edge there, and vice versa. And all of this is checked in, say, quadratic time, right? You just have to check all the pairs of vertices. So it's definitely in NP. Is it? So we knew that problems in NP, they could be of different kinds. So there could be problems which are NP hard, NP complete, which are hardest problems there, probably not solvable in polynomial time. Classic examples include satisfiability of Boolean formula. Also, if a problem is polynomially solvable, there are many polynomially solvable problems. Say 2-set, it's polynomially solvable. It's of course also in NP, because every deterministic algorithm can be interpreted non-deterministic one. Also, you can ask for a hint but not use it. So NP is a subclass. P is a subclass of NP. How about this? How do you think? Is it NP hard or polynomial? Just bold guess. Well, I don't ask you for an answer, for a real mathematical answer, but just what is your guess? Isomorphism. Is it plausible that you can check for isomorphism fast, or is it NP hard? Well, okay, I will give the answer. It's quite a rare species. It's one of these not so many known NP problems for which we know nothing. So we do not know a polynomial time algorithm for graph isomorphism, and we do not know that it is NP complete. So nothing of this is proved. Possibly it means that this is an intermediate problem. So if P is not equal to NP, then we've seen this picture, right? That you have this big NP class. On the bottom, you'll have polynomial. On top, you will have NP complete. Also, there is something in the middle. And there are even formal theorems, I think it's called Ludner Theorem, that if P is not equal to NP, that it means that this situation is non-trivial. Then there should be intermediate problems, which are not NP hard and not polynomial. But of course, this all depends on the fact that P is not equal to NP. So for this guy, nothing is known. So it could be NP hard. So suppose P is not equal to NP, non-trivial situation. If P equals NP, everything is polynomial, of course. So there could be a situation that the graph isomorphism is NP complete, and it's not polynomial. There could be a situation it's really polynomial, but we just do not know the algorithm. It could be the situation that is somewhere in between. So it's not polynomial, but yet not NP hard, which means that the problems like SAT are harder than that. So this is quite a rare species. This problem is, by the way, interesting for, well, not that may be interesting for social network analysis, but as I said, it could be useful for structure mining. That you find, well, we'll discuss subgraphs in a minute. You find a subgraph in the social network, and then you try to restore the structure. But it's very useful in chemistry and in biochemistry by comparing two structural things of some polymers or something like that. This is in bioinformatics. It's also a quite hard problem that you have to check graphs for isomorphism, but this could be hard. The known algorithms, of course, are exponential. For specific kinds of graphs, there are polynomial algorithms, say for trees and for some other versions of graph. So now for subgraph. A subgraph is just a part of a graph which is obtained by taking a subset of vertices and edges. So, and the vertex subset should, of course, cover the edge subset. So if you take an edge, you should take both its vertices. Easier? So for example, this is a graph. This is a subgraph. So we grayed out some of the edges and vertices, and we took this black, which is a subgraph. There is a specific notion of an induced subgraph. This means that you just take a subset of vertices, and you should take all the edges from the original graph. So say our ego networks, this was an induced subgraph of the real Facebook data set, because we took some guys, 10 vertices, we took all their friends. So this was a subset of the huge set of vertices of the real data set. And then we took all the friendship relations between them. So this is an induced one. And a spanning subgraph is dual. It means that you take all the vertices, but maybe drop some edges. So here is a spanning subgraph. All the vertices are taken, but some edges are removed. And the graph became disconnected, for example, here. This is an induced subgraph. So you took only part of the set of edges, vertices, and you took all the edges between them, which were in the original graph. And this is neither a spanning nor induced one. So you took not all the edges, not all the vertices, and on these vertices you took not all the edges. So of course, if the graph is, a subgraph is both spanning and induced, it's just the original graph. You should take all the vertices, all the edges. This is not interesting. So this is, in a sense, dual notions. And what is the subgraph isomorphism is the following problem. You have a graph H and a graph G0, and G0 is called the small one and the H is called the big one, and you determine whether there exists an induced subgraph in H which is isomorphic to G0. Also, there is a version without requiring the graph to be an induced one, so you just find some pattern inside. The search for spanning subgraph is not usually considered a subgraph isomorphism problem because G will be not a small one. It should include the same set of vertices. And it's just the notion of reorganizing them. So why are they called big and small? Well, because it's pattern match in a pattern search, really. So H is the big structural graph of some real-world structure. So it could be social network graph, as we noted before. It could be, say, in biochemistry, it could be a graph of a big molecule or a series of molecules, big protein, for example, DNA. And G0 is a small one, it's a pattern. We wish to find whether inside this big structural graph structure data, there is a pattern which we know. So it's the same as search question, but it's searching not for words, not for something symbolic, but it's searching for graph theoretic patterns. So it's basically the same. And you will have the many applications in the bioinformatics, chemical informatics, and what they call graph mining. So it's the same as data mining, but not for data which is structured as text or strings of symbols, words, but as graph structure then. And in both variants, this subgraph isomorphism problem is going to be NP-complete. Unlike just graph isomorphism problem we don't know, here we have the formal notion of a formal theorem is NP-complete. If P is not equal to NP, then in general subgraph isomorphism is not solvable in polynomial time, but of course specific cases are. For example, you can ask whether, so if the size of G0 is fixed, then it's going to be, of course, polynomial, because it just, but the degree of the polynomial will grow with the growing of G0. So if you have, say, G0 be just of 3 vertices, a triangle, how can you find whether a big graph includes a triangle? Well, you just try all possible triples and see what they form a triangle. So this is a cubic time algorithm. But if G0 has 4 vertices, it will be degree 4. If you have 5 vertices, it will be degree 5. So the degrees depends on the size of G0. And in our, of course, situation, G0 is a parameter. So therefore, this will lead to exponential development. So specific kind of subgraphs, so the clique. A complete subgraph. Here is an example. 4 vertices form a clique. In social networks, it means the group of users who are mutual friends. So, specific kind of subgraph. By the way, a clique, if it is a subgraph, of course, it's always an induced one, because it takes all possible edges. No edge could be removed. A dual notion is an independent set, which is an empty induced subgraph. So no pairs of vertices in an independent set is connected. Here we have red vertices, they form an independent set. No pair is directly connected. Because they have paths which connect them, but direct connections, no. Actual notions of clique and independent sets are dual. And at today's practical class, we'll have a simple problem to dualize them. So, and we'll see that searching for cliques and searching for independent sets, they're polynomially equivalent problems. So if you can solve in set polynomial, you can solve clique polynomial and vice versa. So for independent set, we're going to prove NP completeness. This will be, I think, the first NP hardness results for graphs in our course. So the problem of existence, so we're given the following input. We have G, which is a graph. Well, it should be written in this kind good form. So we have G graph, K is a number, natural number. They are both inputs. And we ask whether G includes a clique of size K. If K is fixed, it's polynomial, right? Because you can just try all these K tuples of vertices. But the degree of polynomial is roughly speaking K. So if K is an input parameter, this is an exponential algorithm. So this is an NP-complete problem. And this is done by the following reduction. You take C and F sat and reduce it to inset. So C and F sat is known to be NP hard. Actually by Cook-Levin and Satan. So Cook-Levin shows that just satisfiability of Boolean formulae is NP hard. And Satan transformations show that the same holds for 3 CNFs, 3 conjunctive normal forms. So here we do not need the fact that it is 3 CNF. It will be okay for arbitrary CNFs, but the fact that the formula is in CNF, it's important. So now, given a CNF A, we're going to construct a graph G and give a number k, such that this G has an independent set of k vertices if and only if A is satisfiable. And on the next slide, we'll see how it works. So here is CNF. It's a 3 CNF, but as I said, it's not that important. And how are we going to construct the graph? So, as you know, the CNF is 5. Here we have 4 clauses. For each clause, we are going to introduce a clique of vertices, which are going to be all interconnected with each other, like this. So each vertex is marked with one of the literals, but the vertex is an occurrence of a literal in a clause. So here you see that there are 2 P's, for example, not P's, several Q's, etc. So these are. So here we have all the triangles and just edges. If we have a clause which is just from one literal, it will be just an isolated one. We have these 4 cliques. And now we add new edges, and these edges will represent contradictions. So if you have 2 vertices in different cliques, and they have, say, P and not P, you will connect them, representing that they are contradictory. I hope that I didn't miss anything. Let's say for P, you will have 2 P's and 2 not P's. So we have these connections. For Q, we'll have Q here, Q there. On top, we have not Q. And not Q contradicts Q. R and R bar also connect. So what does it mean? It means that if we are seeking for an independent set. So how the independent set is going to be constructed here? First, you have to, so the number of vertices will be 4 in the independent set. So this graph says the following. First, you need to take exactly 1 vertex from each clique, right? Because the number of vertices is the same as the number of cliques. And inside a clique, you cannot take 2 vertices because they are connected. Therefore, you should take only 1. Second thing is that these chosen vertices should not be connected by a red edge. So they should not be contradictory. So this means that if you have, say, inside this independent set a vertex marked with P, you cannot have a vertex marked with not P. And this will give you the satisfying assignment. So for example, here, you take, say, these. This is not unique, but you can take this. So you have Q, not R, another Q and P, not P. And this will yield the satisfying assignment of the following form. So here we know about all of them. Possibly some of the variables could be not inside this independent set, neither in positive nor in negative form. This means that they could be arbitrary. So there is no one-to-one correspondence between satisfying assignments and, yeah. So again, here you have the graph. You have an independent set, and you know that if you have a vertex marked with Q in the independent set, you cannot have a vertex marked with not Q there, because such vertices should be connected. They should be in different cliques. They should be connected, and the set will be not independent. So for each variable, you either have either Q or not Q, or you can have neither. In the last case, you just put the value of Q arbitrary. In the first, you just take Q or not Q. And this will be indeed a satisfying assignment, because in each clique, you will have at least this one vertex with the corresponding value. And this will be true. This green vertex will be true. Therefore, the whole disjunction will be true. And the other way around. Suppose you have a satisfying assignment. What does this mean? It means that each clause is satisfied. This means that from each clause, you can take one literal which is satisfied by this assignment, which is made true, right? This choice is not unique, but at least one could be chosen. Otherwise, the disjunction fails. And if you take this element from the disjunction, what happens next? You just put them into your independent set. And this set will be indeed independent because you took only exactly one element from each clique. So it will be of the given size, the number of clauses, and it will be from different cliques. So the black edges will not prevent you from making it an independent set. And there will be no red edges, because a red edge means that you have chosen Q from one clique and not Q from the other one. And this is not possible because you have a value for Q and it could not validate both Q and not Q. This will indeed an independent set. So this is maybe the easiest problem which can be proved to be NP-hard in graph theory. So you can see here how backwards reduction works. So it's not the forward Cook-Levin reduction. That, of course, well, it's maybe not that easy, but you can represent the problem of being existence of a clique by a Boolean formula, right? Again, well, it's an exercise. It follows from Cook-Levin, but it can be not that easy. It's not like, say, representing coloring as we did before. But this is a vice versa thing. We should encode, we should show that this problem on graphs, it's indeed very general. So this problem can encode arbitrary Boolean satisfiability, well, CNF satisfiability. And therefore it can encode arbitrary, how can I say this? Arbitrary NP computation. So we will see more examples of NP-hard problems on graphs, but probably not on the lectures. I will comment on that a bit more. So another famous problem of which is NP-complete is the existence of Hamiltonian path. So a Hamiltonian path is a path, or it could be cyclic, then it's called a Hamiltonian cycle, and it could be just a path that's called a Hamiltonian path, which visits each vertex exactly once. So existence of Hamiltonian path is also a well-known NP-hard problem. So in this course, I think we shall not prove its NP-hardness, because there's also, again, also an encoding of 3-SAT or CNF-SAT. So again, you should now, instead of, say, finding an independent set, you should encode your satisfying assignment as a Hamiltonian path in a specifically constructed graph. This is not that easy. Again, the idea is the same, that given a CNF or a 3-CNF, you somehow construct a graph with the property that the existence of a Hamiltonian path inside this graph is equivalent to the existence of a satisfying assignment of the original formula. The construction is not, I will just post, well, it's already on the web page in the archive. I will just put the link on the top. I will just post on the course's web page a piece of lecture notes which proves this. The proof, again, it's just technical. So, by the way, I have no idea how people generate such things. So when you know the proof, you just have, okay, this is the encoding, and this encoding is established in p-hardness of, say, Hamiltonian path, something like that. But how do you guess this? How do you invent this encoding? Well, it's magic. So, but these are classical results from the middle of 20th century. So people knew this just actually shortly after Cook-Levin, they managed to know this. And this is, it's quite clear, but it's not that interesting. So interestingly enough, Hamiltonian path is a specific case of subgraph isomorphism, but in the sense of not being an induced one. So actually, Hamiltonian path, it's a spanning graph, right? It spans all the vertices. And the idea is that the question is as follows: whether the big graph includes a subgraph, which is just a chain of the number of vertices, which is the same as the number of vertices of the original graph. So this specific case of subgraph isomorphism is actually also NP-hard, and this can be proven. Yeah, let's return to here. Yep. So what we have proved here, we have proved that we have reduced CNF set to int set. Therefore, int set is NP complete, right? So because you have a known problem, so you have it by transitivity, by Cook-Levin and Satan, any NP problem is reducible to CNF set, right? CNF set is reducible to int set for graphs. So this means that any NP problem is reducible to int set by this chain of reductions. Therefore, int set is NP-hard, right? And therefore, for induced subgraphs, subgraph isomorphism is NP-hard. Because if your int set is reduced to subgraph isomorphism by a trivial reduction, you just say, okay, I have a graph. Here it's denoted by G, I will name it to H. And I have a number K. And number K is the size of the possible independent set. And yes, and then I say the following. I take the following reduction. I take this number K. I generate a totally disconnected graph on n vertices. And then I just ask whether it is an induced subgraph of the original graph. And this is equivalent to being an independent set, just by definition. So this means that the problem of finding independent sets it's a subcase of subgraph isomorphism. And even this problem is NP-hard. Therefore, the general problem is also NP-hard. Well, it's NP-hard and it's NP-complete because it belongs to NP. Subgraph isomorphism also belongs to NP because you can just guess the isomorphism. It's just like with graph isomorphism. What about the case of being not induced? So on today's practical class, we'll discuss the equivalence of clique and independent set. That if independent set is NP-hard, then finding cliques is also NP-hard. And a clique, if it is a subgraph, and it's always an induced subgraph. So if you ask just for existence of a subgraph, which is a complete graph, full graph on k vertices, this will be always a clique, and it will always be induced. So this means that having clique being an NP-complete problem, you also show that the subgraph isomorphism, without the requirement of the subgraph being an induced one, is also NP-complete. So this is the comment on two versions of subgraph isomorphism problem. They are, of course, different, but they're both NP-hard. And here in the Hamiltonian path situation, we have another specific case of subgraph isomorphism, which is how can we call it? Which is a subgraph of the following kind. It's a long chain. Or if you want to seek for Hamiltonian cycle, this will be going to be a long loop, long cycle. Okay, in existence of this as a subgraph, which is not going to be induced, it should be a spanning one. But this is not a reduction, this is a reduction in another direction. So if we know how to solve this hard problem, which we know to be hard, subgraph isomorphism, we can solve Hamiltonian path. But Hamiltonian path on itself is also NP-hard. So in this course, we'll omit the proof of NP-hardness, but next lecture we'll start with some application of this stuff to genomics and some understanding of how one can overrun it. So there will be a specific kind of graph for which Hamiltonian path will be reducible to Euler path, and Euler path is polynomial time solvable. So here you see that we always have to balance on the border of interesting problems which are hard and easier problems which are tractable. And sometimes the specific cases of hard problems, they could be much easier. Like 2-sat is easier than general sat. Unfortunately, some problems which were interesting for us to solve, they are NP hard. So this will be another example of NP hard problems in graphs. And on the next practical class, we'll also have the third one, which is recoloring. So again, what we knew for recoloring, so we know that recoloring is reducible to 3-set. Well, we did this manually. You remember that, yes, by encoding the colors by Boolean variables. So we say that this BI is the fact that ith vertex is colored in blue. So this actually follows from Cook-Levin, because 3-set is a general NP-hard problem. Anything which is NP reduces to it. These are stuff also reduced. Maybe not in the natural and easy fashion, but it can be reduced. So, but in order to prove that tricolor is NP-hard, you need to prove the backwards reduction. You need to show that 3-set, for example, or satisfiability, this Cook-Levin example, can be reduced in its turn to 3-set. So this is the correct way of reduction you should perform in order to obtain NP hardness of tricolor. And we'll do this on the next practical class, just as an exercise. For Hamiltonian, it's different. So that's about all for today. The material, well, it was not hard, but it included some speculations on social networking and stuff like that, and also a proof of NP hardness here. Yes, and the second topic for next time will be counting problems and stuff like that. So going beyond the class of polynomially solvable things. So returning to the home assignments, I will maybe return to this slide just to make something visible on the whiteboard. So what are the things which were some organizational moments? So first, we have approached the deadlines for homeworks number 1 and 2. But I would like to remind you, maybe this will be a relief for some of the people, that the deadlines are anywhere on Earth. This means that if at least at some point on the Earth it is still, say, October the 5th, then you are still inside the deadline. In Moscow, this means the midnight anywhere on Earth means 3 p.m. next day, because Moscow is GMT plus 3 and this is GMT minus 12 anywhere on Earth. So this means that the first assignment can be submitted today till 3 p.m. Moscow, and I think then GitHub will just close the possible submissions. And the second assignment is said to be due today, but it can also be submitted by email till 3 p.m. tomorrow. It's also possible. So next organizational moment, the second assignment should be submitted just by email to the official address, sk@myras.ru. Please submit to that email. You could also do it by my email HHSC, but there's not a convenience for me. But I will also read it. So for the first one, again, the preferred way is to submit via GitHub. I would like to remind, and I will write this reminder also in the chat tonight, please, if your nickname on GitHub does not include your name and surname, or your user information on GitHub does not include that, please fill in the Google form, which is also, there is a link in GitHub and also I think on the course's webpage for your identification. So when I see your nickname, I will consult this form, the results of this form, in order to de-anonymize you and understand who submitted it. If you fail to do this, of course, the automatic grader will grade and give you a good mark, but I will not be able to convert it into a real grade in your grading roster. If you see the, it's either on GitHub or, let me just see it here. I will give an answer in a minute. So, and if you take Yep, so you go to the formulation of the task. No, I think it's not, yeah, sorry, it's not on GitHub, it's on the courses webpage. So if you go to the courses webpage, and the link there is on GitHub, the link to courses webpage, and there is an instruction on submitting. So there are several points. Maybe I will show it also here. You can see that here there is an instruction on how you should submit it via GitHub. So, and here is the identification form. And if you open it, you will see something like that. And here you will say your name, nick on GitHub, and this is optional. You can also put your email here if you wish to have some extra identification. So again, on you can still submit it right by now. So here we'll see that how can you do this. So you have to use GitHub account. You accept your assignment via the invite link, which is here, the link here, and this will give you a repository which includes the tests and the testing workflow. So on commit, on pushing your information to GitHub, the autograder will get invoked, and you will get this, if everything is correct, they will get the symbol of success, which will be visible in your repository. If it's so, then you just you are fine, and I will also see it in my GitHub Classroom interface, and I will properly grade you. If you have any questions concerning this, please contact me by email. This will not work if you submit it not in Python, or if you submit in Python 2. So if any failures, sometimes, by the way, for one student it was the case that it did not invoke, then you may overcome it by just making an extra commit. Just commit something meaningless, and this will do the job. So, okay. So far, so good. In any questions, again, please email to me. And after I collect all the grades for homework number 1, and so there are some questions here, I think, in the chat. No, the question was, do we need to use HEC email? No, please submit it to that email which is put here, sk@myRasRule. This will be just more convenient for me. So thank you for understanding. Okay, so after I collect the grades for homework number 1, both sent by email and submitted to GitHub, and after I check homework number 2, I will make the grading table available for you for reading. And you can just look it up and see that everything is properly graded. If the situations happen that it's not properly graded, you will just shoot an email to me. So the deadline for homework number 3 will be next, I think, well, I will propose it formally, maybe it will be next Monday anywhere. In order to finish it before the final class, and on the final class we'll see all your homeworks done. Don't worry, it will be posted tonight, and you will have some time for doing this. It's, again, not hard to solve. So it's quite a short programming assignment. Okay, so if there are any questions, please ask them now. Otherwise, we finish and reconvene in a week.
Степан Львович, можно вот еще вопрос по поводу системы оценивания второго ДЗ? Она как-то изменилась по сравнению с прошлым годом? Просто в прошлом году 6 номеров было, а сейчас 7 во втором ДЗ.
For the homework number 2, the grading will be proportional. So if you solve all the 7, you will get a maximal mark. If you solve nothing, you get 0. And in the middle, well, you will be just the proportion. All the problems in homework 2 have equal weight. In case of fractional ones, they will be rounded to the closest integer. So say if you get from the 4 grades, if after doing this proportion you will get something like, I don't know, 3.6, you will get 4, something like that. And then you can compute it.
Ага, то есть, по сути, мы количество правильных номеров умножаем на 4 седьмых и округляем до целого, да?
Yes, you multiply your result by 4 divided by 7, and then you round it up. If you have, say, something like 2.5, it will be rounded up to 3.
Понял. А можно еще вопрос по формулировке одного из заданий во втором ДЗ? Вы могли бы, пожалуйста, его открыть сейчас? Чтобы я просто...
Let me show the second assignment. Yes, it's here. Do you see it, right? Okay.
Да. Вот у меня вопрос по формулировке шестого номера.
Okay, problem 6.
Я правильно понимаю, что у нас на ленту записано просто какое-то, условное число в двоичной системе исчисления, и без пробела сразу после него оно уже написано, но как бы в обратном порядке.
Yes, exactly. In problem 6, your input is as following. You have a long string of zeros and ones, and the correct input, which you should yield 1, you should yield yes, is as follows. You write some word 0001111, and then just immediately, without any separator, you will have the same which is written in the reversed form. If you have such an input, you should return yes. If you have an input which is not of that form, you return no. So this is basically what is called a palindrome of even length. So any word which is even and which is the same when being reversed is of that form. Exactly.
Понял, спасибо. И еще такой один моментик. На сайте курса я вот не нашел слайды 4-й лекции, там только первый.
Oh, yeah, sorry. I will post them tonight, yes, with the 5th one. Yes, it is just my fault. They will be there.
Отлично, спасибо.
Okay, if no more questions, then we finish right now. And again, for the seminar, Yakov will come to this physical room here, and the online one will be in the other meeting room. So thank you for coming, and we meet in 20 minutes in the seminar room.